Namaste. In this video, we will dive into Geographic Information Systems or simply GIS. We will start with simple introduction to what GIS means and why it is important. Then we will explore the key components that makes up a GIS like hardware, software, data and people. After that, we will look at different functions that GIS can perform such as storing data, analyzing patterns and creating useful maps. Finally, we will learn about the basic data structures used in GIS like vector and raster, which helps us to represent the real world in digital form. By the end of this video, you will see how GIS acts as a powerful tool to connect geography and technology. You may remember from previous videos that Geographic Information System or GIS is a computer tool that helps us to work with maps in a digital way. It can show, manage and study features and the events on Earth's surface. Think of it as like an updated version of old paper maps. While maps have guided people for centuries, GIS can go further. It gives us a smart ways to use spatial data. GIS allows us to make maps that are not still images but dynamic and interactive. With it, we can click on features and see detailed information. We can also study how things are related in space. This ability helps us to answer complex real-world questions. GIS is not just about maps, it is about problem solving. It supports planning, managing natural resources and making smarter choices. Cities use GIS to design roads, track electricity and water networks and monitor transportation and so on. It also helps in protecting the environment, managing disasters and improving safety. In short, GIS connects data with location, making it one of the most powerful tools for many important tasks today. A GIS usually organizes information into different layers, also called themes. Imagine stacking transparent sheets of paper all showing the same place. Each sheet carries different details. One is for roads, one is for rivers, another for soil, another is for land use and so on. In GIS, these layers are stored electronically and all tied to the same coordinates and scale so that they fit perfectly on top of each other. This way you can combine layers and see how features are connected. For example, by placing a land use map over satellite or drone imagery, you can study how farming, forest or cities are shaped by landforms and elevation. This layered view makes complex patterns easier to understand and analyze. The Geographic Information System or GIS is built from four main parts: hardware, software, data and people. All these work together to turn real-world objects into digital information. Once in GIS, we can ask questions, see patterns, and present answers as maps, charts, or reports, or even 3D views. At its core, GIS links two types of data. Spatial information tells us where it is using coordinates. Attribute information tells us what it is by giving details. For example, a tree on a map has spatial data showing its exact spot and attributes like its species or height. The true strength of GIS comes from this powerful link between location on a map and details in the database. This connection makes GIS a smart tool for exploring and understanding the world. The first important function of GIS is data capture. It brings together information from many sources like paper maps, aerial photographs, satellite images, GPS points, or ready-made digital files. The second function is data storage and manipulation. Here, GIS stores data safely in databases, keeps it accurate, and lets us to retrieve it and update it whenever we need. The third and most important function is data analysis. This is where we ask questions, measure distances or areas, and combine layers to see patterns and relationships. Finally, the fourth function is data representation or presentation. GIS allows us to share results as maps, reports, or charts or tables, and even in 3D views. Together, all these functions makes GIS a complete system for working with spatial data. In GIS, we use two main types of data structures, raster and vector. Raster data is like a grid of tiny cells where each cell stores a value such as a land cover or temperature. Vector data, on the other hand, uses points, lines and polygons to show real-world features. Points marks exact spots with no size, like wells or trees and are stored with coordinate pairs. Lines represent features such as roads, rivers, or pipelines made up of connected coordinates. Polygons show areas like lakes or agricultural fields or city zones formed by closed lines. In vector data, every feature has extra details called attributes that are linked to it. A point showing city may have attributes like its name or population or number of houses, etc. A line showing a river may carry details like length of river or water level and so on. A polygon of farmland can store ownerships and its area, etc. Vector data is best for features with clear shape and for making accurate length and area measurements, while raster works well for continuous data spread over space. Both data types are important and together they give GIS the flexibility to represent Earth in digital form. Now let us see how relationships between features are stored in vector data model. There are two main methods called spaghetti data structures and topological structure. The spaghetti model is simpler one. Here every feature, whether a point, line or polygon, is stored separately as just a list of x and y coordinates. In this model, if two lines cross, the system does not know they intersect. If two polygons share a common border, the system does not recognize that either. There is no built-in information about connectivity, meaning how features are linked, or adjacency, meaning which ones are next to each other. For example, if two polygons share the same boundary line, that line gets stored twice, once with each polygon. This creates redundancy where the same data is stored or repeated in two separate data. While the spaghetti structure works for simple map drawings like those in CAD or computer-aided drawing, it has limitations in analysis. If we want to know how features connect or intersect or interact, the GIS has to calculate it every time, which can slow down the work and use more computer power. That is why more advanced methods are often needed. To overcome the limitations of spaghetti model, GIS uses topological data structure. Topology is a branch of math that studies properties of shapes that stay the same even when stretched or bent. In GIS, topology explains how features are connected and related in space. It uses nodes, which are ends or meeting points of lines, arcs, which are line segments between nodes, and polygons, which are closed by arcs. With topology, we can store and check relationships easily. Connectivity tells us which arcs join at which node, useful for tracing routes in road networks, etc. Adjacency shows which polygons share common borders, helping us to see which areas lie next to each other. Containment tells us which features fall inside a polygon, like well inside a property polygon, etc. Proximity shows how close features are, and direction tells us where one feature is in relation to another. Even though it takes more efforts to build, the topological model reduces duplicate data and links features in an organized way. Its biggest strength is that it supports powerful spatial analysis since these relationships are built into the system from the start. Raster data structure divides the area into regular grid, usually arranged row by row from top left corner. Each grid cell holds a single value that represents feature at that spot. This method is simple and widely used for satellite images or remote sensing images. It is also perfect for digital elevation models since nearby elevation values are rarely the same. Raster makes it easier to store and work with remote sensing data, especially when handling continuous surfaces like terrain or temperature. We will learn more about elevation models shortly. Now let us look at fundamentals of databases in GIS or Geographic Information System. A database is simply an organized collection of data, and in GIS, it is often most important and time-consuming part of any project. We use special software called a Database Management System or DBMS to create, manage, and access this data. A spatial database stores point, line, and polygons or raster cells together with their attribute details. Creating a GIS database involves three steps. First, it's spatial data input, where we capture the location and shape of features using digitized maps, GPS, or existing digital datasets. Second is attribute data input, where we enter descriptive details about each features into tables, often from spreadsheets or other sources. Third is linking spatial and attribute data, which is done using unique ID or number that appears in both map feature and attribute table. This linking allows GIS to connect the where with what. Good database design is very important. A well-planned database saves time, avoids repetition, and keeps the data consistent. A poorly designed database can cause missing or duplicate data, confusion in analysis, or mismatched information between maps and tables. In short, GIS uses database to integrate spatial information with attributes or non-spatial data, and with that link, it becomes a strong tool for displaying, querying, and analyzing and managing data efficiently. As we know, GIS works with two kinds of data: spatial data, which tells us where something is, and non-spatial data, which tells us what it is. The first step in GIS is to input this data in digital form. Spatial data can come from paper maps, aerial photographs, or drone photographs, satellite images, or to be collected directly in the field using GPS or physical surveys. Sometimes it is already in digital form, such as digital maps, so which makes it easier for us to use. Non-spatial data usually comes in tables or reports or spreadsheets with descriptive details. Digital data like satellite images or GPS points can go directly into GIS softwares, but paper maps and aerial photographs are not digital. They must be converted into digital format. This happens through scanning or digitization processes. Scanning creates a digital picture called raster image. Digitizing converts the features on these images into vector data. There are two main digitizing methods. Manual digitizing uses pen-like device or special tablet placed on map where each feature is traced carefully. Heads-up digitizing is more common today, where a scanned image is shown on a computer screen and a mouse is used to trace features directly. Another important vectorization where software traces automatically, but it usually needs manual correction. So all these methods ensures we can bring both old paper maps or old maps and modern maps or modern images into GIS for further analysis. Once data is entered into GIS, it usually contains some mistakes. GIS data editing is a step where we correct these to build proper relationships between features and update existing digital maps. This ensures the data is clean, consistent, and ready for analysis. Key tasks includes fixing locational errors, correcting topology, and matching map edges. Topology building, as we learned earlier, means defining how features are connected next to each other or contained within each other and so on. Many GIS software tools can build topology automatically after digitizing. This helps to catch mistakes, avoid duplications of shared boundaries, and saves a lot of storage space. More importantly, it makes spatial queries and analysis faster and more reliable. Topological error occurs when spatial relationships between features break down. While digitizing, some common errors may appear. An undershoot happens when a line fails to meet the line it should connect with. An overshoot happens when a line goes beyond an endpoint. Dangling nodes are line ends that do not connect to anything. Sliver polygons are tiny unwanted shapes formed due to small mistakes when drawing polygon boundaries. These errors can cause problems in analysis if it is not corrected. So most GIS software provides tools to fix them automatically or semi-automatically. For example, the software can snap points together, trim overshoots, extend undershoots, or remove slivers based on the rules set by the user, and so on. Correcting these errors ensures data is accurate, reliable for further use. Locational errors happens when position or shape of features on the map is not correct. These errors usually comes from three sources: georeferencing mistakes, scanning problems, or human errors. Georeferencing errors happens when the wrong control points are used, which can distort the shape or scale of the map. The solution is to choose correct points and apply geometric transformation again, a step called redigitizing. Scanning and tracing errors occurs when lines are too close or too wide or broken or unclear. This can cause collapsed lines, extra lines, or wrongly shaped features. Fixing them may require rescanning the map and carefully digitizing again. Edge matching is another step needed when multiple map sheets cover an area. Because of small digitizing or referencing differences, features like roads may not join properly at the edges. Edge matching adjusts this so they connect smoothly, forming a continuous map. These editing steps may seem basic, but they are very important. They help us to build an accurate GIS database, which is foundation for all further analysis and mapping tasks. We know that GIS uses two types of data: spatial data that tells us where things are, and attribute data tells us what those things are. A very important step is linking between these two data together, and this is done using georelational data model. In this model, every spatial features, whether a point, line, or polygon, is given a unique ID. This ID is the key that connects the map feature to correct row in the attribute table. One column contains the same ID as the polygon, making the link between map and table. When you click a polygon on the map, the GIS uses its IDs to pull out all the details from the table. And if you select a row in the table, the matching polygon on the map gets highlighted. Each row in the table is called record, each column is called field. This linking of spatial and attribute data makes GIS a powerful tool for analysis and decision making. Now let us talk about spatial data analysis. The picture here shows how a plague spread in medieval Europe, with colors marking outbreaks over time. This is a simple example of how spatial data analysis can create infographics to explain a pattern. Spatial data analysis means studying the patterns and relationships we find in geographic data. The main purpose is to discover new information or answer a specific question using the data. GIS makes this possible with both vector and raster datasets. The process is straightforward. First, we use one or more data layers, then we apply spatial function or operation on them. The result is a new layer that stores outcome of our analysis. These results can appear as maps, reports, or charts, or even short summaries. Some outputs help us to see the information more clearly and use it for making decisions. Next, we will look at some of the common types of spatial analysis operations. The first type of spatial operation is a query. A query means selecting features based on a condition. There are two main types: attribute queries and spatial query. Attribute queries use information in the attribute table. For example, we can ask the systems to select all districts where population is more than 10 lakhs. We can also combine conditions like select districts where the population is above 10 lakhs and literacy is about 70%. These spatial queries work with location. For instance, you might select all the polygons shown in the yellow or those with certain area. Another useful operation is dissolve. This merges features that share common attribute. For example, district can be merged into their states by dissolving their district boundaries. This makes the map simpler and allows us to look at the data at larger scale. It is especially useful when working with polygons. Overlay analysis is one of the most powerful tools in GIS. It takes two or more layers covering the same area and combines both of their shapes and the information to form a new layer. Imagine placing a land use map over a soil map, where when overlaid, the polygons are cut wherever they intersect, creating smaller, newer polygons that hold details from both layers. This helps us to see, for example, which land use occurs on what soil type. There are several ways to do overlay. Intersections keeps only the area shared by both layers. Union keeps everything from both and merges data where they overlap. Clip uses one layer as a cookie cutter to cut shapes from another. Merge or append is different, so as it simply joins features from two or more layers of the same type, like stitching two roads maps together. Another key operation is buffer analysis. This creates zones around points, lines, and areas, either outward or inward from the edges. For example, buffers around schools can show which neighborhoods falls within walking distance, and so on. These tools make spatial analysis much more powerful and practical. Raster overlay is simpler than vector overlay. It works by comparing cells in a raster grid and combining their values one by one across layers. For example, in a mathematical overlay, we can add the values of matching cells from one rasters to see combined results, like total rainfall from two time periods. Raster overlay can use logical rules to highlight specific conditions such as areas meeting certain thresholds. Another common step is clipping raster with vector boundary, like cutting the districts out of larger map to analyze only that region. The advantage of raster overlay is that it allows fast, efficient analysis of many layers and helps to reveal spatial patterns. But one limitation is that details can be lost if rasters have different cell sizes or do not align properly. Still, it remains a powerful method for studying continuous data. Now let us understand a special type of vector data called triangular irregular networks, or TIN. A TIN is used to represent surfaces, especially land elevation or terrain. It works by connecting a set of sample points, usually elevation points, with lines to form a network of triangles that do not overlap. Inside each triangle, the value at any location can be estimated from 3 corner points. This makes TINs efficient for storing and working with surface data. They are commonly used to create digital elevation models, also called as DEM. DEMs are very useful for 3D viewing and analyzing surface features like slope or aspect, which tells us how steep the land is, and so TINs play an important role in modeling and understanding the shape of the surface. A digital elevation model, or DEM, is a three-dimensional representation of the Earth's surface. It looks like a detailed 3D map where colors or shades show the height of the land. DEM is a broad term and can mean two different models. The first is digital terrain model, or DTM, which shows bare ground surface by removing trees, buildings or other objects, giving us true topography. The second is digital surface model, or DSM, which includes everything on the surface such as forest, buildings or other structures and their heights. These models are very important because they help us to understand variations in elevation and are used in many applications like mapping, planning and environmental studies. GIS works by representing features from the Earth's curved or three-dimensional surface into a flat map or computer screen. This process is called map projection. Since a sphere cannot be perfectly shown on a flat surface, distortions in their shapes or area or distance or even directions can occur when we are representing on a flat screen. No projections can preserve everything at once, so the choice depends on what the map is really meant for. The graphic here shows how some regions look stretched on the world map because of choice of a projection. This is why different regions use different map projections to suit their needs. There are three main families of map projections. Cylindrical projections wrap a cylinder around the globe. Conical projections place a cone over the globe. Planar, also called azimuthal projections, place a flat plane against the globe. Each method preserves certain properties better than others, helping to minimize distortions for different purposes. Map projection is therefore a fundamental step in GIS for making accurate and useful maps. Different map projections are designed to keep certain map properties accurate. Conformal projections preserve shapes and angles, which is useful for navigation. Equal area projections keep the size of the area correct, which is important for land use or political maps. Some common projections in GIS are the Mercator projection, a cylindrical type that keeps angle but makes regions near the poles too large. The transverse Mercator is also cylindrical but placed sideways, making it suitable for mapping regions that stretch north to south. The Lambert conformal conic is a conical projection often used for mid-latitude regions that extend east to west. The Albers equal area conic is another conical type, keeps area sizes accurate and uses for studying land use or natural resources. In GIS software, the system usually assigns a projection automatically based on location. However, the users can change the projection to match project needs or to make different datasets easier to compare. Choosing the right projection ensures that maps are clear, accurate, and suited for the purpose. Closely related to projections are coordinate systems, which gives us a framework to define the location of points on the Earth. In GIS, we mainly work with two types: Geographic Coordinate System or GCS and Projected Coordinate System or PCS. A geographic coordinate system uses a spherical model of the Earth and defines positions with latitude and longitude. Latitude measures how far north or south a point is from the equator, ranging from minus 90 degrees at the south pole to plus 90 degrees at the north pole. Lines of latitudes are also called parallels. Longitude measures how far east or west a point is from prime meridian, which passes through Greenwich, UK. Longitude values ranges from minus 180 degrees to plus 180 degrees. These coordinates are measured in degrees and they locate a point on globe very well. However, they do not work perfectly for measuring distance or area on flat maps because the size of 1 degree of longitude changes with latitude. A projected coordinate system solves this by flattening the Earth with the map projection. It uses x and y values on a grid, often in meters, which makes calculations of distance and area much more accurate. The Universal Transverse Mercator or UTM system is one very common projected coordinate system. UTM divides the world into 60 zones, each 6 degrees wide in longitude, and applies a transverse Mercator projection on each. This system is widely used for global mapping. For example, India lies in UTM zones 42 to 47. These coordinate systems makes GIS powerful tool for precise location, measurement, and analysis. Another key concept in GIS is the datum. A datum is like base model of the Earth that we use to measure locations. Since the Earth is not a perfect sphere but an irregular sphere called geoid, we approximate it with smooth, slightly flattened surface shape called an ellipsoid. A datum tells us how this ellipsoid is placed in relation to the real Earth. It provides a starting reference so that we can define latitude and longitude accurately. Different regions use different datums to fix their areas better. For example, WGS 84 is a global datum widely used around the world, especially with GPS system. In the past, India often used the Everest datum for local accuracy, though WGS 84 is now more common. Choosing the correct datum is very important. So if the data layers use different datums, they may not line up properly, causing positional errors. That is why all data in a GIS project should share the same datum and same projection for consistency and accuracy. Without this, even the most detailed maps can look misaligned. Datums ensure that our spatial data matches real world as closely as possible. Okay, now let us understand the term digital cartography. Cartography means the art and science of making maps, and digital cartography means making maps using GIS software. It is not just about displaying data, but also about designing the maps and communicate information clearly. This involves choosing the right symbols, colors, and labels for the features, and adding elements like scale, direction, base maps, and navigation tools. This must be arranged neatly so that the map looks good and easy to read. GIS software provides many tools for this. It allows us to make high quality maps that show analysis results efficiently. One important part is the map scale, which shows the ratio between the distance on the map and distance on the ground. A good example is a Bhuvan geoportal developed by ISRO. It allows users to view navigation maps, natural resource data, and thematic maps such as land use land cover maps. This is a classic example of how digital cartography in action, and I encourage you to explore it and see different kind of GIS maps in the Bhuvan geoportal. So why GIS is so useful? First, it supports better planning and decision making. GIS combines data from many sources like maps, satellite images, GPS, or census tables, even if they were created in different formats. It put together into a single system, making comparison and analysis much easier. For example, when planning a new road, GIS can show the terrain, the land ownership, nearby population, and environmental issues altogether. This helps planners to compare options and choose the best one. Second, GIS gives us powerful visual analysis. Maps made with GIS not only attractive but also informative. They simplify complex information much better than reports or tables. GIS can also make 3D models, elevation maps, and virtual fly-throughs, which are very useful for city design, building roads, and planning parks, and so on. When people see data clearly, it becomes easier to explain, share, and decide. Thirdly, GIS improves teamwork. In organizations, usually different departments keep separate data, leading to repetition and confusion. With GIS, all teams use same spatial data, so updates by one team benefit everyone. This saves time, reduces errors, and improve communication. So that is why GIS is so useful and powerful today. Also, GIS saves both time and money. The starting cost of software and computers may be high, but in the long run it pays off. GIS automates map making and data analysis, and because departments can share same data, work is not repeated. It also runs analysis quickly, so decisions are made faster and with more confidence. Another advantage is better data management and accessibility. Paper map gets damaged and hard to update and takes a lot of time and space. GIS stores everything digitally, makes it easier to update, share, and access anytime. With internet-based GIS and mobile applications, even field workers or citizens can use maps directly on their devices. Finally, GIS is database driven. Unlike traditional maps that just show shapes, GIS links points, lines, and areas to detailed information. This lets us to search, filter, and analyze and discover pattern, making GIS truly smart and powerful tool. That is the end of this video. Namaste.